We can use deep learning in various different contexts. However, many of the biggest success stories that you've seen are for a family of machine learning problems called supervised learning. And most of the algorithms that are relevant to multi-object tracking also belongs to this family. To give you a sense of how these deep learning algorithms might work, we here provide a brief introduction to the basic principles that underlie supervised learning. Supervised learning is a family of machine learning problems where we seek to predict an output from an input. A classic example of this is image classification, where the input could be an image of, say, a cat, and the output is the class label, cat. Another input might be an image of a dog, for which we want to produce the class label dog. Supervised learning is generally approached in a data-driven fashion, where we first collect a dataset, preferably a very large dataset, with inputs x and the intended outputs y. Given the dataset, we then train our algorithm. Specifically, in deep learning, we select the parameters theta, describing the weights and biases in our neural network, such that our neural network predicts the output in the best possible manner. Once we have selected the weights, we are ready to use our neural network F to predict the output for new and unseen data X. Apart from image classification, another important example of supervised learning is machine translation, for instance, from German to English. In this case, you would like to collect a large set of examples with German sentences and the intended English translation. Object detection, that we discuss in more detail later, can also be formulated as a supervised learning problem, where we might collect a large dataset of images along with all object detections in these images. Let's look at the data-driven approach mentioned above and discuss how we can find the parameters theta in the neural network F. Suppose we have both training data and a loss function L. The loss function can take different forms depending on the problem, but it should measure the error between the value of f and the value of y. We'll discuss different loss functions shortly. Given a loss function, it would be appealing to minimize the expected loss. However, since we generally can't minimize the expected loss, we normally try to minimize the empirical loss instead, which is the value of the loss function L averaged across all our training data. This can of course be seen as an approximation to the expected loss. A very nice feature with this approach is that we have transformed the supervised learning problem into an optimization problem. For instance, perhaps you are trying to do image classification. Using the empirical risk, the problem of classifying images has been simplified to finding the parameters theta that minimize j of theta. Once we have solved this optimization, we can use the obtained theta vector and our neural network F to classify images. To minimize j of theta, we typically use some type of gradient descent algorithm that has been modified to fit the above problem formulation. This may sound challenging, but there are well-established algorithms and software that simplifies this task immensely. To better understand the above description of the empirical risk, it may help to describe commonly used loss functions. Suppose we are trying to solve a regression problem, such that the interpretation of f is that it's an estimate y hat of y. If f and y are vectors, we can for instance use the squared distance between the two vectors as loss function. If we use this loss function, the empirical risk approximates the mean squared error. That is, we would try to find a neural network that gives the smallest possible mean squared error, which may seem like a reasonable approach. Considering how important classification problems are, I'd like to mention the cross-entropy loss, which is the standard loss function for classification, even though that may be harder to grasp. For this description to make sense, you need to assume that we are using a softmax activation function, such that AL becomes a probability vector. Given the true label y and the probability vector AL, the cross-entropy loss is minus the logarithm of element number y in the vector AL. This may look a bit involved, but we can observe a few different things. First, in order for this loss to be small, we want ALY to be as large as possible. This can be understood from the figure, and the fact that ALY is a probability and thus takes values between 0 and 1. Second, the interpretation of element number y in AL is the probability of that class label according to our neural network. The cross-entropy loss therefore tells us that we want our network to output a large probability for the true class. Hopefully this seems reasonable. Again, please recall that we used this loss to define the empirical loss, and our network therefore needs to trade off the losses for all the different samples in our set of training data. What I've presented here is by no means a complete introduction to supervised learning, but I hope it gives you a first idea about how we may proceed to train our neural networks to solve supervised learning tasks.